So it's 1:30. We can start, I guess. So yeah, hi everyone, and welcome to this course, Mathematics Inspired by Quantum Field Theory. Um, okay, so can you hear me well, first of all? Okay,
Yes.
perfect. Yes. All right, so I suppose you have read those two announcements I put on Fields LMS. So basically, the the logistics of the course is pretty straightforward. I don't think I have to go through that. But if you have any questions, you can send me an email and I'll be happy to discuss it with you. So that should be okay. So pretty much we're going to start today right away with the course. Yeah, one thing I want to say is by all means, feel free to interrupt me and ask questions. That's absolutely important to have some dialogue, interactions going on. So yeah, make sure to do that. Okay, so I thought I will just start with yeah, first of all, are there any questions? Okay, cool. Okay, so I just start with a rough sketch, a kind of very concise outline. So this is outline of what we plan to do. So this course has three components. In the first part, we will deal with Feynman graphical calculus. So it has the following items. So we discuss Gaussian integrals. Then we discuss Laplace and the steepest descent methods. Laplace and the steepest. Actually, I would say stationary phase approximation, that's better. Stationary phase approximation. Then I will discuss perturbative expansion of exponential integrals. Exponential integrals. Is that readable, what I write on the board? Is that okay? Okay, great. Yeah, so then we'll discuss loop expansions. And then applications to graph graph counting. Applications to graph, or mostly it's going to be these actually to graph counting. Okay, so that's like a first component of the course. The second part, we will build on what we learned here, and then we'll discuss random matrix theory basics. random matrix theory. So this is R and T. So we start with a famous example, which is Gaussian unitary ensemble. GUE. This is so-called Gaussian unitary ensemble. Discuss that. So then we'll have genus expansion. So in the first part, we learned that these exponential integrals per se are related to graphs because of expansion over summing over graphs. They emerge. Here in the second part, we'll see that actually exponential integrals with matrix elements, so matrix integrals, so to speak, can be expressed in terms of summing over Riemann surfaces. So it's a two-dimensional version of this first part. And that's why we call it genus expansion. So the genus of the surface appears. And there is also this map, the so-called map enumeration. Which is related to that. Then we learn some techniques of RMT, like orthogonal polynomials. Polynomials. Yeah, so somehow on the way we will prove. So here is two continued. On the way we will prove something like Wigner's semicircle law, which is a famous theorem of random matrix theory. This is like a central limit theorem of random matrix theory. So that's very important. Wigner's semicircle law. Yeah, and then for the third part, which is the last one, we will start discussing applications to this random matrix theory or matrix integrals to finding something about a cohomology of modular spaces of curves of Riemann surfaces. So that's, I can erase this, I suppose. That's the third part of the course. Part 3. Applications of what we learned in the second part. To finding something so sort of topology of modular spaces of curves. Of complex curves, which are essentially Riemann surfaces. I mean, this is this famous Harrer-Zagier theorem. Harrer-Zagier theorem. Okay. I mean, that's already quite a tall order. If we manage to do all this, and if there is some time left, then we'll do even more. So we may look at actually some very simple quantum field theory models But then there are so many things you can do. I mean, this subject is, in terms of its breadth and content, is infinite. Really, you cannot possibly cover everything, but even not nearly. But we'll try to do something. In terms of references, I gave a couple of references. One is, I think of
Excuse me, may I ask a question about the outline?
yes, yes.
Do you also like plan to like cover some applications to like let's say knot theory as an example?
That would be also a possibility, because yes, I think you have Chern-Simon theory in mind, maybe.
Maybe
Yeah,
like
that's
John's polynomials, like the written.
yeah, Jones
Mm,
polynomials. Yeah, I'm not planning to do that, but if there is, I mean, that's like a wonderful topic for a presentation, actually.
I see.
If because Chern-Simon theory again is a quantum field theory, so and it has applications to yeah
Got it.
to knots, or you can do basically other types of topological quantum field theories and applications to Jones
Right.
polynomials. So those are
Right.
all possibilities. I won't do that, but
Mhm.
yeah, will
I see.
that's a good topic, actually. Yeah.
Thanks.
Okay, sure. So adding of notes. So there are two versions of this. The one version he posted like a few years ago, and then the second version he posted like last year. I will follow the first version, which is more concise, and for me is easier to follow. The second version is double as much, and there is so much stuff there. I mean, it's I mean, both are wonderful writings, highly recommended. So I will follow this with adding maybe double F, with adding some extra stuff maybe, but highly recommended. There is also for the random matrix theory and map enumeration, elementary aspects of it. So there is this book by Londo and Swankin, which is very good. Um, I forgot the title of the book. Do you remember? Graphs on surfaces. Yeah, something like graphs on surfaces. But there is a book by Einar. It's called Counting Surfaces, which is much more advanced and elaborate because it's all about topological recursion. Okay, so this is counting surfaces. So if you want to do for a project something like topological recursion, which is much deeper understanding of this map enumerations than what we do, then this is a fantastic reference for that. Yeah, I guess there are some notes by Ken Yates as well. Um, also lecture notes. This is supposed to be very good as well. So, uh, but I will be really relying on the first edition, first version of I think of notes. I have posted most of this stuff actually in resources, so you can access them easily. Okay, so I think that's basically the the course outline. Are there any questions or? Okay. So I think I can erase this now and I start the course proper. All right, so before I get into technical stuff that we are going to cover, let me just say a few words about classical and quantum field theory basics. So that would be helpful. Classical and quantum field theory. Basics. So this is kind of motivation for why these methods actually were discovered to start with. Most of these things were discovered by physicists, so we should know what was the motivation and why it was discovered. At least at a very, very, very elementary, very kind of basic level. Okay, so first of all, what is classical field theory? So you have this X, which we call it a space-time. It's a smooth manifold, basically. It can have extra structure, like a complex structure, symplectic structure. It can have Riemannian structure or none of those. But to start with, most of the cases, this is a smooth manifold. Even for a standard model of elementary particles, which is a huge achievement of theoretical physics, X is just R4. So you don't even have to know any manifold theory to get into some very, very deep waters with this thing. So X is R4. Then you have a space F, which is the space of fields on X. So as a first approximation, this could be maps from X into R. It could be maps into complex, then would be complex fields, or some vector space. Okay, so etc. There could be real value maps, complex value, or vector value. In general, could be even sections of a vector bundle over X, or sections of the vector bundle on X. Vector bundle X. It could be even maps from your space-time manifold X into another manifold. So that would be a kind of nonlinear field theory in that case, or maps from X into another manifold Y. So nonlinear sigma models and stuff like that. Okay. So this is a space of your space of fields. And I'm very vague about what kind of maps. Is it continuous or C infinity or what the smooth orders? These things, for the physics of it, at least at the first approximation, really doesn't matter much. So we really want to get some objects to start working with, and then what is needed, it will be suggested as we go on. Okay, so this is a space of fields, okay? And then we have something like called Lagrangian. So this L is a map that to each field associates a density basically on X, two densities on X. And then using this, you define something, I mean, physicists, classical physics, you define something called action, S, from F to R. This is called action, which is defined by integrating this density over the space-time X. So S of phi is equal to integral of L of phi over X. Again, whether this is integrable over X or, existence of this could be subject to a separate investigation, but for us, it doesn't matter. For actual physics, doesn't matter much. So this is called action. Now, the main thing about, there's a question. So there is a question. Okay, yes. What do we mean by densities on X? So I suggest if you want to ask a question, or you can unmute yourself and just ask it in case I miss your question. If I don't check the chats, then if you express your question verbally, then I won't miss it. Okay, but now this time I got it. So what do we mean by densities on X? So a simple kind of density, for example, imagine X is an n-dimensional manifold, right? The density could be an n-form on X. So a density is an object that makes sense to integrate over X. Now, if it is an n-form, and the manifold is n-dimensional and is oriented, we know that we can integrate an n-form over the manifold. But it doesn't have to be like that. If the manifold is not oriented, then there are more general objects called densities, which are like absolute value of dx instead of dx itself or dnx itself that you can integrate. Is that okay? Did you get the idea? In public library, so I'm unable to speak. Okay, so no, that's good. Okay, that's good. Thanks for asking the question. That was a great question. Yeah, excellent. Okay, now, so this is the action. Now, there is this principle, which is called principle of least action, which kind of, it's really amazing, right? Because it just says that all of physics, more or less, all of physics, okay, there are areas which is not covered by this, but most of physics, I would say, is covered by one principle, which is the principle of least action. It's an amazing achievement. And this was obtained by, this was actually postulated by Hamilton after a long period of discussions, investigations, examples by many mathematicians, starting from antiquity to Fermat, and then Maupertuis, and then Lagrange, and then Hamilton kind of formalized the whole thing. So this is Hamilton's principle of least action. Least action. So I say least, but we really don't mean least. We mean extremum action, I should say, or critical action. So basically, it just says that. So we have discussed all possible fields, and now the question is physics distinguishes, classical physics distinguishes one field among all possibilities. if you know everything that you need to know, like the energy, I mean, the initial velocities, momentum, and all these things. If you want to know the future of the system, you have to know how fields evolve in time. And this principle says that basically, this is the Hamilton's principle of extremum action. The actual physical trajectories, so to speak, of fields that are followed by any classical system satisfies this differential equation. Of course, this differential this equation should remind you of equations that you have for extremum, minimum, maximum, extremum of functions of one variable or several variables from calculus, right? So because we have like f prime of x equal to 0, that's for one variable functions, and gradient of f equal to 0, etc. This is a huge generalization of this. It's infinite dimensional, you'll see. And it's not in this case, you get some algebraic equations, but in this case, you get differential equations. So then what happens is that basically all equations like Lagrange equations in classical mechanics Maxwell's equations yeah, I mean, Einstein's field equations Yang-Mills equations. These are all examples of this. So you just have to write the right form of action, find the right form of action. To start with, you have to have the right Lagrangian, then you get the action, and then all these equations. Also, I should say, maybe even here, I should say Bain equation, actually. These are all examples of this. I mean, in the case of Bain equations, it's this equation, right? dt squared minus v squared Laplacian x of phi equal to 0, right? It just tells you how a field phi t or vague phi t and x will change in the space-time. And this is the Bain equation. And this is an example of this, actually. I won't write down the Lagrangian for this case or the action, but this is a standard, and you can just learn it in any textbook. Okay, so this is classical physics, but we know that the world is not classical, it's quantum. So then the question is, how to quantize this this thing. Are there any questions about this, by the way? Okay, so this is classical physics, and we want to go to the quantum case, quantum version of it. So how to quantize this? More or less, there are two methods to quantize. One is called canonical quantization. which I won't discuss. It's a standard method. It's more complicated than this functional integral quantization that I'm going to discuss. But the second method is due to Feynman and Dirac. Feynman and Dirac. Okay, so yeah, functional integral quantization. So in this approach, you say, okay, so first of all, there is this quantity z. It's called partition function. This is defined like this. This is by definition integral over all fields, exponential of I over h bar s of phi d phi. So this S is the classical action that we discussed. So this is classical. F is the space of all fields. And d phi is a measure, is a mysterious measure. Nobody knows what it is. Nobody knows how to define it. And perhaps even doesn't exist mathematically on the space of all fields. And you have to calculate this integral. This is called partition function. But I mean, this integral is ill-defined in many ways. I mean, this integral is ill-defined. I mean, this quantity, this is a purely imaginary number, right? It has absolute value 1. This quantity has absolute value 1. This space is infinite dimensional. So you are integrating a function that has always absolute value 1 over an infinite dimensional space against a measure that we really don't know what it is. And so it's quite, so now I just have to, okay, so I think the camera now moved somehow. We have to, that's completely off balance now. You know, okay, no, you know what? We can manually.
But then we'll keep moving again, right?
Really? It shouldn't.
Okay, we'll see.
Is it on?
If it does not move, then we're good.
Why did it move? Okay, so that's okay.
Yeah,
that's
a
okay.
little bit more.
Yeah, looks okay now. Okay, right. So this integral is very problematic, but nevertheless, physicists could use this to do the most precise calculations in science that has ever been done. So this is really amazing. Is the kind of least precise mathematical gadget, which is this, and I will tell some more, has been used to do the most precise calculations. For example, the anomalous magnetic moment of the electron. You can calculate using this, I don't know, maybe 13 decimal digits. That's the most precise calculation in science. So it's quite mind-boggling, right? How such imprecise kind of mathematics can lead to such precise calculations. Okay, so well, I mean, we'll see that the way to proceed is we will consider finite dimensional versions of this. Okay. And then, if you want to do the actual physics, you move by analogy. Okay. So, so here I just write here work by analogy. What do I mean is that first, define Z in the finite dimensional case. And that's what we do in this course, actually. And then, by analogy, so here you get the recipe that we'll get to this recipe in a couple of lectures. And then the recipe actually kind of makes sense in infinite dimensions in the actual calculations. It's not quite precise even then, because then you have to do even a little more kind of brushing sort of infinities under the rug, but it's still better than starting with this. Okay, so that's basically they will approach this by analogy. Now, this is not so. If you know this quantity, basically you can calculate everything. But one of the things that you want to calculate. So let me just write it here. This is the so what is an observable? So an observable is just a function on the space of fields, right? Okay. So this is good. Yeah. Or C or etc. Well, basically it has to go to R. Has to be real value. Yeah, right. And then from here you define these quantities, which is called like F1, F2, Fn, which is called which is basically 1 over Z integral F1 of phi, F2 of phi, Fn of phi, e to the I over h bar s of phi d phi. Right? So this has different names. It's called correlation functions. Sometimes it's called 10-point functions. Endpoint functions. Or scattering amplitudes. It has many names. But basically, and the goal of a quantum field theory is to compute these quantities, because these are the quantities that they can measure actually in lab. And that's what you want to compute. And in terms of, this is not quite, because we define 1 over Z, this is not quite a probability distribution because it is complex valued, but it's almost like a complex probability distribution. And these are like moments of this probability distribution function. So to know a distribution is more or less same as knowing all of its moments. So that's why through access, you cannot access the probability distribution directly itself. We don't know what it is, but we compute its moments by calculating such integrals. Okay? So these integrals are called exponential integrals. In general, in mathematics. Okay, so now, so how does this relate to classical physics? Classical physics. There are some principles that we will discuss in detail. The principle says that, again, went back to that. No, I will do it now. Okay. That's funny. It's moving, yeah. Again, the principle says that the bulk of the contribution to the integral comes from actually the critical points of S. Okay. Okay. So the main sort of part of value of this star comes from the critical points of S. So in other words, the S again delta phi equal to 0, right? So that's the equation that we had in the classical physics. So basically, well, we'll discuss that in detail, but basically, what we're going to do, we're going to write this. We cannot calculate it, by the way. Definitely, we cannot calculate this. But what we're going to do is we'll show that there is an infinite series where the first part of the series starts with the value of S at phi 0. So imagine there's a solution here, phi 0, and S of phi 0 essentially is the main component of this calculation that comes from that. So if you want, like in the case of classical physics, classical mechanics, so if you are in like classical mechanics, what
I think it's just following you. If you're
now it's following me actually. Now it's gone into that mode. That's okay. That's yeah. So in classical mechanics, we know that the Euler-Lagrange equations between any 2 points, more or less, if they are close enough, if they are not very far, there is a unique path. Okay, so this is the critical path, right? This is critical path. But if you want to do the quantum mechanics, this principle, this Feynman's recipe says that actually other paths also are going to contribute to expectation values and to everything. So in classical mechanics, we were very prejudiced because we said that there is only one path, and that's the critical path, more or less unique if the 2 points are close enough. It's like a geodesic on a Riemannian manifold. If 2 points are close enough to each other, there's a unique geodesic connecting the two, right? Of course, if they are far apart, there may be infinite geodesics, like on the antipodal points on the sphere. There are infinite geodesics, there are infinite critical paths between the two. But if they are close enough, there's a unique one. But in quantum mechanics, this is only first part of the perturbation series. And then these all paths also contribute. So, and this is sometimes it's called the democracy of paths or democracy of fields, because there's not one field that matters. All fields matter. So this is democracy of paths. Okay. Now, for technical reasons, it's much easier to work with not this case with imaginary numbers. It's better to work with the Euclidean version. So let me write it down. So this is the Euclidean path integrals. So these are Euclidean path integrals. So in this case, we are working with quantities like this exponential of minus s of phi over h bar d phi. Okay. is this one, and but these are easier to discuss or to define because you can imagine this could be, for example, a positive definite function, and it has a minimum, so it has sort of better convergence property, although it's still divergent, but it's divergent in a less dramatic way than the imaginary version, which is the Minkowski version. And in physics, usually you start with this, and then you do a complex so-called weak rotations. So weak rotation. I won't discuss this, but that's the relevance of the two. So from Euclidean metric, you go into this one. So phi over h bar d phi, you go into Minkowski metric. And the actual physics, quantum field theory, is with Minkowski metrics, of course. It has to be relativistic invariant. But you start here. So this is like dx squared, dt squared plus dx squared plus dy squared plus dz squared. Euclidean metric turns into negative dt squared plus dx squared plus dy squared plus dz squared, by the weak rotations, the map T to IT. Oh. Okay, so now making the whole thing kind of short. So we are to discuss such integrals in purely finite dimensional case. So what is the finite dimensional version of this? So this is over all fields, right? So what we are going to do, we are going to replace this now. Okay, I erase this part. By a finite dimensional integral, which is integration over Rd, d-dimensional Euclidean space, exponential of minus s of x over h bar dx. This is like d-dimensional volume 4 on Rd. I just don't put d here, just dx. Huh? Where s now goes from Rn or Rd to R is action function. Right? So S is action function, and so what happens? So we replace F, space of all fields, by Rd, right? So F, remember, it was maps from some space X into R. So here you can imagine that what is X here? X is a discrete manifold with endpoints. The space of maps from endpoints into R is just Rd, right? So this is like maps from this space 1 to N, D to R, right? So we have made this X, so this is our X. So we have made our X completely discrete and finite, and then you get into this situation. And the amazing thing is that the recipe that we'll obtain to deal with this case actually turns out to be extremely effective in dealing with this infinite dimensional version as well. But again, we won't discuss that much because this is more mathematics based. So we want to understand this. Of course, now we can discuss for which functions S from Rd to R, this integral is convergent because we are over Rd. This is Lebesgue measure. This is really calculus. And we will discuss this from next lecture. And we will obtain the recipe for computing. We cannot compute this, of course, in general, but we will write something called asymptotic expansion of that integral. And then we'll see that this can be expressed as summing over graphs. So that's our first goal. All right. I think this was just supposed to be a motivation for why we are interested in such integrals and where they come from. I mean, in mathematics per se, also, of course, exponential integrals are extremely important. I mean, for many reasons. But this was the physics background that I wanted to say. I think that's good now. Are there any questions? I don't see any questions, but if there are questions, please. Before we say goodbye for now, because today was just 1 hour.